And then looking at the surface-based CAPE and SIN comparison, this is actually a huge factor in what was going to occur. We're seeing a surface-based CAPE around 5,000 joules per kilogram in southern Minnesota, moving into western Wisconsin with time, and actually really not seeing a whole lot of SIN, only about 25 joules per kilogram. And we're still really looking at how the movement of the storms are actually remaining along the low-level instability gradient as they're pushing further east. Next. So just to quickly step through, so these are the observed soundings from the Minneapolis office. So they actually did 4 soundings that day. And with time, you can see how the CAPE values are just continuing to increase. We're seeing that extreme instability. We're also seeing the steep mid-level lapse rates. We're seeing more moisture start to deepen, as well as those strong mid-level winds. And actually, we're also seeing how there's really not a whole lot of I should say capping going on with time. We're seeing it slowly diminish. Next. And just to point out, so this is the 0Z sounding from MPX, just to do a quick comparison to the sounding that was in Green Bay. There's about 5,000 joules per kilogram of CAPE, and that is at a maximum for the compared to climatologically speaking anyways, for Minneapolis. And if you switch it to the Green Bay one, we can see that there's still a decent amount of SIN over the Green Bay area further to the east, and we're not really seeing that cap breaking anytime soon. So we did see it break further to the west in Minneapolis, but obviously we're still dealing with that here in Green Bay. Next. And just to also look at another sounding analysis, this is at Rhinelander. You can see with the yellow dot there, this is just north of where the blowdown area was. And we are seeing the low-level destabilization occurring with time. We're also still seeing the resemblance of that cap pretty much staying in the area, but we're also seeing the favored shear profile that's actually more favored for supercell type mode coming into play, which actually does play an interesting role, as we'll get to later. Next. So just to look at the expectations, it's quite obvious that SPC did have a pretty good idea of what was to come. We also were anticipating this to be a major wind threat, as you can see from the middle graphic. And actually, the moderate risk was updated in the morning. We were actually in an enhanced risk to start the day, and then they did upgrade us to a moderate risk. And just to point out, taking a quote from the one of the day one outlooks, is that strength of the vertical shear suggests the potential for intense bowing segments capable of yielding a derecho with significant widespread severe wind gusts. So clearly, we were anticipating the potential for the widespread straight line damaging winds, and even there was a PDS also issued in addition to a severe thunderstorm watch. But I will turn it over to Gene now, and he'll take you through more of the radar as well as the damage images.
Okay, thanks, Rebecca. All right, so we'll start here with just looking at the radar snapshots, and just briefly touch on the cams and just the HREF in this case. So what we're seeing here in the large image there is the HREF paintballs. This is valid at 21Z at 4 p.m. About the time the storms are organizing over east central Minnesota. And overall, if you look at the paintballs, the HREF, this is the 12Z run of the HREF on the 19th. It generally captured that area over east central Minnesota fairly well, as you can see in the circled areas. One area it didn't capture so well was the convection further downstream over northwest Wisconsin. There's really no indication of that in any of the HREF members, at least from the 12Z run, which is what we were looking at as the data was evolving here. And that's interesting because I'm going to show you now exactly where that convection over northwest Wisconsin originated from. Before I do that, this is just the 01Z forecast valid at 1Z, same 12Z run. And if you look overall, the CAM members basically had the convective mode. It was in the ballpark. And I thought really the HRW components, CAM members, probably handled it the best just in terms of the general location, the general character, convective mode, particularly the HRW NSSL. That's in the dark red. It seemed to do a little better on the overall structure and the timing, yet it was still a little slow overall, which is probably not to be unexpected with a durational type system evolving. But the CAMs didn't do a bad job. Our main question that afternoon was exactly where across the north half that would be impacted. So what I'd like to do now is talk about the radar evolution of the primary blowdown on July 19th. So we're going to do that next. So this is a 22-hour animation, starts in the morning of the 19th and goes through the overnight and into the next day of the second event on the 20th that we'll be talking about later. Note the convection over eastern Minnesota, rapidly moving eastward, present bow echo developing. Apparently it leaves some sort of convective outflow boundary. And then another area of convection rapidly races across the Fox Valley the next day. So that morning, that first area of convection with the blowdown likely enhanced a synoptic boundary across east central Wisconsin, in which the next day's bow echo and QLCS occurred. So the two events were somewhat related in that regard. Another thing to notice too, real quickly when the loop starts, is note how that lead supercell, once it merges with the QLCS, the very rapid development of the surge and then the bookend vortex. Very, very interesting evolution. So let's look at that lead cell that I was talking about. As I mentioned, the CAMs did not have a good handle on the convection over northwest Wisconsin early on in the afternoon. We see that convection originated over the western Dakotas earlier in the morning and gradually moved into Wisconsin during the course of the day and the afternoon, and eventually the organizing convection over central Minnesota merges with that supercell, and during that merging process, bam, you see the very impressive surge that occurs. So a very interesting convective scale interaction here that appeared to lead to the primary intense surge. Here's the storm relative animation. This is from GR2. I had to do this manually, but I just wanted to show you the evolution during this merger process. So on the left is that lead supercell for northwest Wisconsin. It was very obviously long-lived, persistent, as you see here. And then eventually that supercell gets engulfed by the upstream QLCS. And once that merges, we see the initiation of that intense surge into Langlade County right there. What I thought was kind of remarkable, going back and looking at some work that Ted Fujita did in 1978 when he did that famous study of the 1977 July 4th blowdown in northern Wisconsin. If you compare his schematic of the radar evolution to what we're seeing on July 19th, remarkable similarity in what he's describing there. It's almost uncanny how he describes that lead supercell becoming the northern end bookend vortex, leading to the intense surge. So very, very interesting similarities here. And this is just the base velocity storm relative corresponding to the reflectivity data, again showing the persistent rotation with that lead supercell. As Rebecca showed, the environment in that area was the shear width profile was quite favorable for a supercell structure. So it's not surprising that we see this discrete supercell strengthen and then eventually merge with the QLCS. That image on the right there is one of the tornadoes that occurred. There were two that occurred with the lead supercell, not with the QLCS. And that was in northwest Lincoln County. It was, I believe, an EF0. It wasn't a particularly intense tornado, but it did produce a tornado. The second one occurred right about the time of the merger in southeast Oneida County near the end of the loop. That also dropped a EF0 tornado just at the time of the merger there. After that point, it became pretty much a massive surging QLCS and derecho. Okay, this animation is storm relative as well, and what I have overlaid on this is the damage swath. You can see that by the arrows. I'll talk more about how we obtain that, but what I want you to pay attention to is the location of the echoes and how the damage swath corresponds to the evolving QLCS. And I think one thing that you'll see is after the merger, you note the surge, and then you see the bookend vortex, and then you notice the tail of the bookend vortex. So it looked like the primary damage swath was associated with that southern end or the tail of the bookend vortex. It almost sort of reminiscent. It reminds me a little bit of a sort of a sting jet type of phenomena that more on the synoptic scale, but it kind of has that feel to that, this intense bookend vortex, comma head, the surge, intense reflectivity notch with the inflow jet, all coming together. And again, the damage was remarkably corresponded quite well with the tail of that mesovortex. By the way, the maximum inbounds during the peak of this event was on the order of 122 knots or 140 miles per hour at about 5,000 feet roughly at this range from the Green Bay radar. So very, very interesting evolution there. I had talked with, after the event, I had talked to a couple individuals that try to get some idea what they actually experienced. So I had talked to a gentleman in Mountain, Wisconsin, and that's that circled area. He had actually rode out the storm at the ambulance service where he worked. And he was waiting for the storm to pass, and then they assumed they were going to have to go out and do some, likely have to respond to perhaps some injuries and so on. But he described, unsolicitedly, he said, Gene, what was amazing about this was the winds lasted like 20 to 30 minutes, and the strongest winds seemed to occur near the end. And this was the radar image about the time he was experiencing that. So he basically described it as hurricane force winds that lasted a really long time. And I'm going to just click on this. And this is the video that he had sent me as he was waiting out the storm. So this is just a small snippet of what he experienced. Again, this is about the time of the radar image in the mountain area, right near that apex of that northern bookend vortex. So again, he's experiencing this for at least 10 or 15 minutes. This was after the primary surge came through initially, probably about 10 minutes earlier when the leading line came through. So another storm relative animation, and I just wanted to point out at this point that there wasn't a lot of obvious mesovortices embedded within the line north of the apex. There were a few weak transient circulations, but they didn't last very long, except for one, and I'll talk about that in a minute. Our overall warning operations, as you might have expected, given what the SPC outlook was we were going to focus on the damaging straight line wind threat with potential for extreme damaging wind speeds, and we were going to avoid trying to chase down any embedded mesovortices. So we pretty much, we did just issued severe thunderstorm warnings with high-end wind impact wording. This is the corresponding velocity data, and I just want to point out the one mesovortex that sort of stood out. What's interesting is you'll see how it evolves. It sort of forms near the apex of the bow, and then it gradually falls back to the northwest, becoming part of the northern bookend vortex. That's kind of an interesting interplay between the mesovortex and the larger vortex to the north. But what I wanted you to point out was as that mesovortex falls back and merges with the bookend vortex, you see on the left, you see kind of a resurgence in the dry slot, or a considerable drop in the reflectivity. So you see that occurring, sort of like a a rear inflow notch type of thing, kind of resurging or redeveloping up there during that merging process. And you also see on the right, there's a secondary enhancement in the wind speeds. You see an uptick in the inbound velocities back up to close to about 110 to 150 knots as that merger takes place. So it's, again, an interesting interplay and interaction going on between these smaller scale mesovortices and the primary dominant northern bookend vortex. So just very interesting evolution there that I wanted to point out. So now to talk about some of the damage with the bookend with the primary blowdown. And this is a map that was prepared by the Wisconsin Department of Natural Resources and the U.S. Forest Service. This is based on aerial surveys. They did several aerial surveys over several days in the week or two following the blowdown. And I wanted to point out that, again, the blowdown that we're talking about, it was just one of a couple of areas of significant damage. Primarily, if you look to the west in the Rice Lake area, there was a significant area of blowdown there too. That was a little earlier in the afternoon, a little to the south of the evolution that we just discussed. I'm not going to talk about that in this event or in this presentation, but I'd like to go back and look at that a little bit more closely, because as you can see, there was significant damage. I should mention too, in the graphic, what you're seeing here is the percent tree fall. So the colors represent the percentage of trees down based on a subjective aerial survey and subsequent photography. So basically the areas in reds and oranges indicate anywhere from 50 to nearly 100% tree fall in the area that was surveyed. As you get into the light blues and greens, obviously lesser tree fall in the area surveyed. That ellipse on the bottom there, west of Green Bay, that was the next day, and we'll talk about that. And that was mainly a tornadic damage there. You can see it's much more widely scattered in this case. So here's just a close-up of that blowdown area. Again, the percent tree fall. Again, you see long swaths of nearly 100% blowdown of the trees from the Pickerel area to Oconto in this area here. The area near the town of Mountain looks like there's no damage there. There actually was. For some reason, that wasn't included in this initial analysis. But that damage path was continuous really all the way to the southeast part of your image. If you look carefully, you kind of see this light, faint path in the background. That actually is the track from the old 2007 EF3 supercell tornado that impacted that area several years ago. It's that scar still remains today. It's just kind of interesting to see how these two events sort of cross there in northern Oconto County. So this is sort of interesting. Our preliminary wind analysis. This was done by our WCM, who is now retired. He did this a couple of weeks after. This is very preliminary. Just a basic idea of the wind speed estimates. Again, this was preliminary and likely underestimated based on what we were able to look at since over the last several months. Easily, I think some of the winds in the primary blowdown area were in excess of 100 miles per hour. We're going to go back, look at the damage survey images, look at some high-res polar orbiting images, and so on, trying to get a better handle on the type of wind speeds we're talking about. So I hope we have a more detailed map of the damage and the intensity of the damage in the coming months. By the way, the eastern half of this blowdown heavily impacted the Chickamaguan-Nicolet National Forest, and this is the southern part of that area. And just to indicate, they did a very detailed survey map, again, from aerial surveys. You can see, again, the areas in the red and the yellow and orange, nearly 100% blowdown, severely impacting that area. In fact, as of late December, when I talked to some of the folks from the DNR, over 200 miles of roads were still closed as of the end of the month, with including miles and miles of snowmobile trails that they were trying to clear before the winter. So that was just in that one area alone. So what I'd like to do now is just make some comparisons, looking at some of the polar orbiting high resolution imagery that we were able to obtain. So what we're looking at is just a before and after animation, and you can clearly see in that inner polygon where the primary damage swath was. From Pearson, southeast to Mountain, you can clearly see the scraping and the scarring in that roughly 60 to 65 kilometer length. Outside of that, of course, there was some more scattered, isolated wind damage. So let's just look at this a little bit more closely from the satellite perspective. So we'll look at that far northwest corner first. This is about the time that supercell was beginning to merge. And again, if you're looking at that before and after, this is before and after satellite comparison. You can see these brown, lighter brown shaded areas. These are areas of blowdown. You see other areas near Pearson. And then south of there, a broader area of more linear type tree fall, kind of narrow paths of tree damage associated with this event. So kind of a interesting damage pattern, at least from the high-res satellite imagery. Here's a couple of photographs from that area just to illustrate. These are microburst type features, very small areas of tree damage, probably a few hundred yards. None of the houses that I was able to see in the vicinity of any of the photos I saw were really impacted other than tree fall. I didn't see any houses actually damaged directly by the straight line winds. It was all trees falling on them. Here's another example in the same general area of the trees. I saw a lot of anticyclonic type pattern to the tree fall. Interestingly, if you look in that in the lower left-hand part of that image, you see that structure there and how the trees sort of change direction behind that. And I suspect that perhaps that structure had something to do with maybe how the winds blew around that structure. I'm not sure, but it kind of looks that way. Even in that structure to the right part of the image, you see some of the tree fall kind of more towards the south. Again, to the back side of that structure. So I suspect that probably the structure has impacted the tree fall to some extent, perhaps. Here's another example, a different area. Again, you see sort of an anticyclonic kind of pattern with the tree fall. And notice on the other side of this road, hardly any trees down. Very interesting pattern. I thought this was interesting. In the same general area, we see these little narrow corridors of trees. Not more than maybe 25, 30 feet wide or yards wide. Almost looks like kind of drainage flow or something. But you see these narrow corridors of trees down. Very interesting. And I think in Fujita's paper back in the 70s, he described, I believe, similar types of damage. And I think he associated these with like smaller scale rotors, I believe he put it, but just odd, tiny scale, small scale circulations contributing to the overall character of the damage. Just very interesting. So we're going to look at the main blowdown area now. We're going basically from Pickerel to southeast of Lily. Just focus on that. And this is a high-res satellite image showing that area. And it's very interesting. You see two primary areas that are completely scraped in the brown areas. Almost looks like somebody took a spackling knife and just kind of dragged it across the landscape. You also see an area of scattered damage to the northeast with that arrow. That, I believe, was associated with that mesovortex that we talked about as was merging with the primary bookend vortex. It appeared that was associated with that. We need to go back and look at that a little more closely. This is just a close-up of some of the areas that were scraped, just to give you a feel for it. These areas are roughly maybe 2 to 3 miles in diameter in general. Here's another example, a little further downstream in the primary blowdown area. Long swaths of 5 to 10 mile areas completely scraped, again about maybe 2 to 3 miles wide. And again, this area to the northeast, southwest of Mary Lake, that appeared to be associated with that mesovortex that we saw, the only dominant one that we really saw during this event. Now I just want to take you quickly through some drone footage of the primary blowdown area. This was done by the Pickerel Fire Department and rescue a few days later. I won't play through the whole thing, but I just want you to get a feel for the character of the damage. And these trees look like, I'm not sure, some sort of maybe redwood or white pine. Their trunks aren't very large, maybe a foot or two in diameter. They tend to be top heavy, so probably more susceptible to blowdown. But overall, they're generally blown in the same direction towards the southeast. and many of the damage patterns were somewhat divergent or anticyclonic in nature. So I'll just let this run for another couple seconds here, just again to give you the feel. Again, if you look at the trees, they're not massive. These are almost look like plantations of trees that were snapped and blown down in isolated areas. Here's another area along the highway. I believe this is 55. And then finally, if you go to the end, if you look to the north, and as we approach the area, interesting structure here, we kind of see this area of flattened lower shrubs or trees kind of feeding into an area of complete blowdown to the north. Very interesting damage patterns here. And then we just kind of rotate around here. You see some more of the damage. Again, little pockets of trees flattened and other long corridors of damage. Here's just a few more images. This is towards the end of the primary blowdown area, just to be complete here. Again, this is near the mountain area, near the latter part. Again, you look at the toggle to the left, you see the blowdown and the scraping, a little bit more scattered than what we saw earlier upstream, but still very obvious in the satellite imagery, and the photo in the upper right is in that general area. And the arrows indicate the general area of tree fall in these pockets of damage. Here's another one. The white circle represents a lake. I forget the name of it. And that corresponds to the satellite image on the left, just to give you some perspective. That we're looking at that area west of that lake, kind of inside that red circled area on the satellite image on the left. Again, that's all blowdown just to the west and southwest of there. And south of there. Here's another image, the same area. Again, that lake I talked about is near that airplane wing support there. Again, you see the blowdown going on for miles downstream. So now I'd like to just quickly touch on the second day, round two. And I'm doing this mainly because I think it offers an interesting contrast between the previous day's QLCS. So this occurred 12 hours later in the morning, roughly between about 9 a.m. and noon. And this event, it was a QLCS at an intense surge, but it was associated primarily with mesovortices. So this is the map of the tornado tracks. This was done by our WCM, Jeff Last, before he retired. And again, the map on the upper left is kind of highlighted there just to give you the idea. Mainly EF0 to EF1 damage. I had surveyed many of these, and I have to be honest with you, was not that impressed with the damage. I mean, EF1 damage is a big deal, but I was expecting a lot worse based on what we saw in the radar imagery and the strength of some of the circulation. This was the expectations we had that morning. I was expecting to go out on a damage survey on this day, the day after, and I was called early in the morning, before 7 a.m., and asked to come in to perhaps work the radar, because it appeared that there was a significant convection already developing over the southern Minnesota, far western Wisconsin that we may have to address. Overnight, I think the expectations were that on this day, the primary convection and severe convection would be more to the south. As you can see in the SPC outlook, this is their 6Z outlook. It was updated and shifted north in the subsequent outlook, but this is kind of what we were anticipating early in the morning at the beginning of that day shift. You can see how the wind damage and the tornadoes were a little bit further north than what we were expecting. So now I'm going to stop there. I'm just going to turn it back to Rebecca and let her just briefly touch on the synoptic environment associated with this second day's event.
Hi, thank you, Gene. So a little bit different compared to the previous day, but still, as you can probably tell, the atmosphere was able to destabilize, and we were able to get more storms that turned out to be more tornadic. So just to quickly go through the analysis, we're looking at the surface analysis. The main thing to point out here is that we do see an increase in dew points. So there is a bit more moisture, low-level moisture that is feeding into central Wisconsin, into that highlighted area. The red highlighted area is our main focus. Obviously, the gray box is actually where the blowdown occurred the previous day. And then the red dashed line is actually where there is a boundary kind of left over from the previous day, which will play a big factor in this day. Next. So looking at the surface-based CAPE compared to the previous day, we're not seeing as much CAPE, but we are seeing more SIN. So there's about 100 joules per kilogram of more SIN. We're also looking at how the south of the said boundary is actually destabilizing along the boundary. So we're looking at more elevated storms forming along this boundary and the instability gradient. Next. So just to look at the observed 12Z sounding from our office in Green Bay, we do see that there is still the elevated CAPE, but we're also mainly looking at how there is a decent amount of SIN there, still about 400 joules per kilogram. And keep in mind, this is a little bit further east than where these storms actually did develop and cause damage. Next. So compared to the previous day, LCL heights were actually quite low in comparison. There was about 600 meters for the LCL heights, and actually it was at a climatological minimum for LCL heights for the Green Bay area. So we're looking at more of the tornadic type development anyways, just because of those lower LCL heights. Next. And looking at the 500 millibar winds, the mean wind from the HREF during the morning, you can see how there is a slight increase in winds associated with the main shortwave that's moving in with this system. But in addition to that, we're also seeing how there is a decent amount of 0 to 6 kilometer bulk shear that is actually across the northern portion of the forecast area, about 40 to 60 knots. Is what we're looking at. Next. And then to look at the 0 to 3 kilometer shear, and then you can see the radar is overlaid on top of it, so you can see the complex of storms starting to move into the area. But the main thing to focus on is that the magnitude and direction of the 0 to 3 kilometer shear was actually more favorable for mesovortex genesis relative to the approaching complex of storms and essentially QLCS. Next. So just to do an overall comparison, main differences with the blowdown, there was a decent amount of greater magnitude of deep layer shear and immense amount of CAPE. We're looking at about 5,000 joules per kilogram with that. And then to compare to the tornadic event for July 20th, we did see the lower LCL heights, but we also did see more SIN on the tornadic day. And mind you, 3,000 joules per kilogram of CAPE is nothing to, of course, not speak of, but there still had to overcome the convective inhibition. But just to identify the similarities between the two, there's actually still a decent amount of lapse rates, steep lapse rates, about 8 to 8.5 degrees Celsius per kilometer. And in addition to that, they both actually propagated along the instability gradients. And actually, the main part of the tornadic event was actually that it had pretty much contributed to more of the well-defined boundary that the QLCS ended up following along, and which actually could have favored for more vorticity and eventually for it to be more tornadic. So I'm going to turn it back over to Gene and he's going to go through the radar animation from July 20th.
Okay, thanks, Rebecca. So just quickly looking at the RAP, Oshkosh sounding there between 13 and 17 Z in the morning. Again, as Rebecca, mentioned here, you see the atmosphere was a little bit worked over the night before due to the overnight convection that is basically weakening over that area. So you see some reflection of that elevated warm and trial air, but that's quickly eroding away. We see the low levels are very moist, up to about 850, at least based on the RAP, becoming unstable very quickly. And also you see the winds steadily increase with high, almost unidirectional, at least down in that just south of that boundary, which is indicated on the left. This is just approximate location of it. You can see even in the radar imagery, you see lines of convection and new cells developing sort of along that. So that would be an indication of some sort of discontinuity there that we clearly saw in the instability, the surface-based instability that Rebecca showed earlier. You look upstream then, you see the convection rapidly congealing and starting to move into the CWA. And when I came in the office and we briefly had a discussion, we were aware that, organizing QLCS with a boundary downstream, watch out. Though we were also concerned about the convective inhibition, what role would that have, and would we get tornadoes? We just weren't sure. So anyway, this is kind of what we were thinking going into this. So I'll go ahead and advance. And interestingly, this is at 10 a.m., just as the convection is entering our CWA, there were two QLCSs. The first one is the main one that was developing rapidly, and that would be the primary one, but you also notice a secondary one just upstream. That had developed further upstream, I think over the Minnesota area, perhaps further west. It was weakening as it was approaching western Wisconsin, but it was moving faster than the lead QLCS. Perhaps it was more elevated. I'm not sure, but the point is that these two QLCSs eventually merged, with that second one merging into the back of the forward one, and that resulted in the intense surges we'll see next. So after the merger, see this intense reflectivity notch develop, very impressive, and then a very intense forward surge ensue after the merger. Again, illustrative of just a very interesting storm scale interaction that occurred in this case as well. Recall in the first one, it was a supercell merger. In this case, sort of a QLCS line merger. In both instances, the result of the interaction results in an intense forward surge. The difference in this case, of course, is there was likely a downstream boundary, and you see evidence of that in the isolated convection developing downstream, and then the bow echo taking off, propagating along or in the vicinity of that boundary. Very, very classic QLCS evolution, really, in this case. In this 4-panel, just focus on the top two. This kind of shows the evolution a little bit more. You see the rear weakening QLCS merging with the primary one, and notice in the upper right, two rimful jets. Discrete rimful jets appear evident initially, and then they congeal with time, and then we get the intense forward surge thereafter. By the way, the forward propagation of that lead system nearly doubled to about 60 knots subsequent to this interesting merger. Here's just a close-up of that, again, showing the entire evolution. We eventually see a northern bookend vortex, a very small, compact rotation in this case, not much different than what we saw the previous day with a very broad, large northern bookend vortex. And I found that to be interesting. Is why is the character of this bookend vortex so much different than the last one? And just an interesting question to think about, just the difference in structure alone. Again, this thing's moving about 60 to 70 miles an hour. And this then is a storm relative animation. Again, following the apex of the bow. Again, this is classic in every way. You have this lead bowing structure. You see convection merging with it. You see the bookend vortex forming on the northern end. You see these little bumps or nubs forming near the apex and then falling to the northwest into the northern bookend vortex. Very interesting. Here's the corresponding velocity. Again, classic. Note the mesovortices forming near that red square, near the apex. Several of them developing in succession and then falling northwestward, almost feeding that little larger scale bookend vortex to the northwest. This is classic. And note that these mesovortices are forming in the balanced portion of the line, where the 0.3 kilometer shear was about 260 at 35 knots. This is about as classic mesovortex evolution that you can get. Keep in mind that this, based on the Green Bay sounding and so on, the environment was relatively elevated, and we still got some tornadoes out of this. And I'm not sure why that is, other than perhaps this was such a strong surge, and these circulations were very strong, but they weren't able to quite do as much damage because of the convective inhibition that was present. We saw something similar to that back in August of, I think it was 2013. We had very strong circulations. We had TDS signatures, yet in some of them the damage was somewhat underwhelming, and perhaps it was just the nature of the boundary layer in this case. We're not sure, but it is interesting nonetheless. Here's an example of two of those mesovortices that had TDSs, reflectivity on the left, base velocity on the right, storm relative lower right, and then the TDSs on the lower left. Again, these developed in the balance region. TDSs were clearly evident. The deepest TDS is around 5,000 feet, not bad at that range. The circulation strength was 35 to 40 or 45 knots, which is pretty decent at that range. Yet when we went out and did the survey, the damage was, there was tornadic damage, but it's really not what we had expected to see. And again, that may play back to the boundary layer, and it's somewhat more stable. So just to quickly summarize then in the last couple minutes, for the July 19th, we had that pronounced shortwave, anomalously strong, mid to upper level winds. The Genesis region was characterized by a strengthening low-level baroclinic zone. In advance of that shortwave, we had extreme instability in the warm sector south of there. The storms developed and moved basically along the downstream instability gradient that Rebecca talked about, near the edge of that cap, essentially. The intense forward surge and the intense wind damage appeared to have been initiated by that supercell merger. Again, that was very similar to what Fujita shared in his 1978 classic paper. The primary damage, the primary blowdown area based on the survey, appeared to align very well with the tail end of the bookend vortex. In that case, there were mesovortices, but they were weak and transient, except for that one mesovortex that we talked about earlier. With the environment on the updraft, downdraft convergence zone was generally shear dominant in this case. Over 300,000 acres of forested area damaged over the northern part of the state, which continues to present a fire risk for RCWA, not only for this fall, but in the next year, because much of that timber is going to be drying out and become a risk. And we are working with the DNR and the Forest Service, provide enhanced DSS in those blowdown areas. I should also mention quickly that the polar orbiting high-res data really is useful, particularly in these type of events. We have large blowdown, large area of damage. It really came in useful just to get a general feel and character of the extent of the wind damage. There's no way you could possibly have done a ground survey here. So with the aerial survey, with some help with the satellite imagery, I think it really gives us at least a better idea of the overall general characteristics of the blowdown. On the 20th, just to highlight some of the primary differences, was we had very low LCL heights. We had a notable amount of convective inhibition, so the environment was primarily elevated, yet we were still able to get some circulations. You can imagine along the leading edge in the balance region of that second event, it's very mechanical. These circulations are driven kind of mechanically, and that mechanical lifting, so to speak, was able to, work against that convective inhibition and still give us tornadoes. But fortunately, they weren't as strong as they could have been, perhaps, if there was less convective inhibition. Again, storm interactions were critical into the intense forward surge that ensued. In this case, it was a line merger instead of a supercell merger that we saw in the previous case. I think I'm going to leave it at that. If you're interested in this day, this two-day event, if you go to this link, this was a link to the Bow Echo workshop in March of 2020. A presentation similar to this. There was also a presentation done by Tom Hultquist, who did some modeling work on this event, and also from SBC they gave a talk about some of the challenges in forecasting this, particularly on the second day of the event on July 20th. That's all I have. Thanks to everyone who helped us out put this together, and I'll stop right there. Thanks for your time.